get in quickly. It was failing again and again. Sorry about that. So let's get on with our lessons then. Regarding the midterm exam, the Viva may have questions related to the fuselage, your fuselage design also. So be ready with all those things. It will be group by group. I'll individual Viva, but I'll finish for the first group, then come to second group, things like that. Okay. So whatever you have done in your assignment will also be there in Viva. What is there in your design? What have you done? There may be questions on that, plus your general knowledge of the design process, plus your basic knowledge in anything you have studied in the previous 3 years. Okay, last class we saw this explicit technique. Okay, can we start, Sanjay or
Yes,
anyone?
sir.
Okay.
Sir, share the screens.
I have to share the screen, yeah. So last class, just hold on a second, please. Sorry about the interruption. So we saw what was explicit and implicit approaches with an example of 1D heat conduction equation. An explicit approach, the left hand side, the unknown is at time or n plus 1th time step, depends on the known values at the nth time step. If we start at t is equal to 0, using that we can get for t is equal to 1. Then using the known values of t is equal to 1, we can get time is equal to 2 and so on and so forth. But in an implicit approach, as if you go by a different discretization scheme, the right hand side would contain terms which are not known yet. Now if you write this for all I, you will get a simultaneous equation involving connected variables. If you solve these equations simultaneously, you will get the solution at all points at the n plus 1 time step. So this approach is implicit approach. We saw the advantages and disadvantages of explicit and implicit approaches. Then we are looking at stability of explicit methods. Stability is important for explicit methods. Implicit methods also need stability analysis, but generally they are stable for a larger time step. So it doesn't need so much worry like explicit method stability. So stability analysis is more important for explicit method. Now again, coming back to the same 1D conductor equation, discretized by FTCS scheme, forward in time, center in space, we sought for the exact solution of the FDE, okay, and letting the numerical solution you have, they call it as the sum of the exact solution to the FTE plus the error. Okay, with that, we noted that the exact solution should satisfy this equation. Okay, so we can cancel out the exact solution terms. What remains for the error? So the error also looks like the same equation. In other words, the error should satisfy the original FDE. This is the conclusion we got. Okay. Now it's time to analyze whether this is stable or not. But before that, we looked at the the condition stability criterion. For stability, the error should decrease with time, which means modulus of the error at n plus 1 time step by modulus of by n plus nth time step should be less than or equal to 1. So, to find this, to see whether this simple criterion is satisfied, we go back to earlier expression. See, start with, let's examine for this FDE. Okay, written for the 1D heat conduction equation, FTCS discretization. This is the error equation. So now, here you substitute for error epsilon of x. Okay, how error varies with x. Okay, on y you have epsilon at a given time step. At a particular time step, how does the error look like? Typically, it may look like jagged like this. So we can approximate it by a Fourier series, which is sigma am e power I kmx. Now error is the real part. So the above e power I kmx, you can put cos kmx plus I sin kmx. Which means you are going for a cosine Fourier series. Then we are looking at Km. What is the wave number? Nothing but 2 pi by lambda. How many waves are there in the domain? That will give you the highest frequency wave which can be fitted into your domain. So the highest m which you can go for this error expression. So the more number of grid points you have, the higher your m is going to be, or more accurate analysis is going to be in other ways. Anyway, we are going for to get some idea about the error. So this is for the total length, the longest wavelength, okay, or the smallest frequency will be this one, which is 2 pi by L. The next one will be 2 pi by L into 2. There are two waves here, so frequency is 2 fitted into the Km is 2 fitted into the same domain, and so on and so forth. So you can see how many number of wavelengths can be fitted in your grid. Suppose grid has n plus 1 grid points. The smallest wave will be between I minus 1, I plus 1. That is the shortest, that is the highest frequency you can accommodate in a grid. So the minimum wavelength will be L by n by 2, which is 2L by n. So the minimum wavelength is 2 delta x. Minimum wavelength is 2 delta x. Okay. So delta x is equal to L by n. Okay, we know number of points by n. We assume a uniform grid for simplicity. Okay. Now this Km is again by definition 2 pi by lambda. You substitute for the smallest lambda, you will get the maximum K, maximum number of the maximum frequency or the maximum number of waves can be fitted in this domain. There's 2 pi by L into n by 2. 2 will cancel. So pi n by L will be the answer for Km. This is what we saw last class. Let us go to the next one. Any doubts in whatever we did last class? Is it clear? Swaroop,
yes,
all? Yeah. Swaroop, clear? Swaroop, Yalini? Okay. I assume it's very clear. So we continue. The epsilon x as a function of x can be approximated by this. M is equal to 1 to n by 2. N by 2 is the maximum value M can take in the grid, correct? So you can't have a frequency which is more than that. Although theoretically the frequency can go up to infinity, this is the best we can do to approximate the error in that grid. So AM, this amplitude can vary with for every M, and e power I kmx. So you will have high frequency errors and low frequency errors in a combination of that. We call them when km is low, we call them low frequency errors. When km is high, we call them high frequency errors. Remember this. We'll come back to this when I am explaining the multigrid. We'll finish this first. So the coefficients AM can be functions of time. Okay. Somehow the time should be factored. So we can write this as epsilon is m is equal to 1 to n by 2 of AM, which is a function of time, into e power I kmx. So we are actually telling that the amplitudes of these different frequencies will not change with time if the grid is fixed. We are not looking at adaptive grid now, looking at simple fixed grid for 1D. So if the grid is fixed, then Km is not going to change with time, but the amplitude can change with time. What matters for us is the amplitude. Amplitude should reduce with time. So errors tend to grow for unstable cases or diminish for stable cases with time at an exponential rate. So we are approximating this AFMT by e power small a into t. Okay. So we can write this as product of two exponential terms. Okay. So generally it has been observed that the errors tend to grow or diminish at exponential rate. Okay. Now the small is a constant, a is a constant which can be different for different m. So in practice we a subscript m, we are taking, generally we are giving a. So for every m, this a can be different. That is what he is telling, but it's not putting the subscript am here to avoid confusion, to make sure this is function of time only. This is function of space only. Now, if you look at the other look at the FD, there is the error, the error forms an FD, the error should satisfy the FD. Yeah. Here, imagine if all this is substituted by those terms, then each one of that frequency will have a separate FD. So all these errors, their Fourier components also individually should satisfy this FD. So let us examine just one term of the series. So if we can draw some conclusions about that term, we can draw a conclusion about generally all the terms, because M is a representative term. So examine only one term, which is M, error of M, that is the mth component of the series, which is a function of x and time, function of space and time. That is e power at into e power I kmx. Now this should also satisfy the original FTE. So we substitute, instead of error, we substitute this term in the original FTE. Okay. Okay. Now dividing this one, sorry, I'll just mute my phone. It's not some problem with phone. Okay. So this should satisfy the original FDE. Let's divide everything by e power at and e power I kmx. You please do this exercise yourself. Okay, be careful with the mathematics. Okay. Now this will cancel, e power at will cancel, e power I kmx will cancel. You remain e power a delta t. That is the first term here. Divided by alpha t, then minus this one. This will be 1 by alpha delta t. Okay. Then here they will cancel. You will get e power I km delta x. Here you will get just minus 2. Here you will get e power I km minus delta x. Okay. So if you simplify this, you will get this expression. E power a delta t is equal to 1 plus alpha delta t by delta x whole square to e power I kmx plus e power minus kmx. So e power a delta t is equal to 1 plus alpha delta t by delta x whole squared into e power I km delta x plus e power minus I km delta x minus 2. Okay. It's a representative term. Now cos km delta x is actually e power I km delta x plus e power minus I km delta x by 2. If you look at this, so this term on the right hand side, you can express it as cos of km delta x. Okay. You can expand this. If you are not aware of this, you can expand this. Okay. And you can cos theta plus I sin theta. E power I theta is cos theta plus I sin theta. Here cos theta minus I sin theta. The plus I and minus I will cancel each other. You will get 2 cos I theta, 2 cos theta. Okay. So divide by 2, you will get the cos km delta x here. So now e power a delta t you can simplify using these two terms. You can simplify using that. Okay. Minus 1. Now sin squared km delta x by 2 is actually this one, no? 1 minus cos km by 2. 1 minus cos 2 theta by 2 is sin squared theta, theta by 2. Sorry, 1 minus cos 2 theta by 2 is sin squared theta. Because for cos 2 theta, you have the formula, is 1 minus 2 sin squared theta. Using that, you can derive the expression. So again, you can substitute for this as minus sin squared km delta x by 2. So any doubts so far?
No, sir.
Any doubts so far?
No, sir.
Okay, okay. Yayani, she's not there, huh? Okay. So, Yayani, any doubts?
No, sir.
Last time when I called you, you did not answer.
I came to unmute, sir, but then you went to the topic, so
Oh, okay. Anyways, how about Swaroop is there? Swaroop? He's not there. Okay. Sivakumar? Okay. So you'll get the e power a delta t is 1 minus 4 alpha delta t by delta x squared to sin squared km delta x by 2. I am warning you, this derivation is a little bit involved and you have to refer back to the earlier one. So please go through it once more or twice more so that you remember this. Now, when you take the ratio of this error at n plus 1 time step and error at n time step, okay, when you take the ratio, you will get e power a delta t. Okay, look at this expressions. Yeah, instead of t, you put t plus delta t, you will get e power a into t plus delta t here. So when you divide by the earlier term, what will remain is e power a into delta t. This is what will remain. Okay. Now we have seen that this is nothing but 1 minus 4 alpha delta t by delta x squared into sine squared km delta x by 2. Now for this to be stable, this error should be, modulus of this error should be less than or equal to 1. Okay. You can also call this whole term as g. So if modulus is less than or equal to 1, either whatever is inside the bracket should be greater than 1, or the negative of that can be less than minus 1. So we'll look at these two cases now. Okay, modulus should be, sorry, this should be less than 1. Whatever is there inside the bracket is less than 1. This will give the condition that 4 alpha delta t delta x squared sine squared km x by 2 is greater than or equal to 0. Now sine squared theta is always greater than or equal to 0. So this is satisfied for any value of delta t and delta x. Okay. So this is satisfied, or this is not a critical condition. Okay. But for the next one, which is stability criterion, okay, this inside one should be greater than or equal to minus 1. It is, see, for when you take the negative one, the sign will become greater than or equal to here. Okay, because minus, if it is greater than minus 1, its magnitude is less than 1. Okay. So look at this carefully. If you don't understand, look at this again, time and again, get it cleared, either through your friends or from me, whatever you prefer. I want you to learn, that's all. Okay. If you rearrange this, you will get the condition that alpha delta t by delta x squared is less than or equal to half. Now this puts a restriction on your condition. Okay. Now if you should be satisfied for stability. So delta x and delta t are not independent of each other. For a given value of delta x, there is a maximum value of delta t. So if you have a smaller delta x, delta t should be even smaller for a stability. Okay. Now this method described so far is known as von Neumann stability method for explicit schemes. You can use it for other equations also, other FDEs also. So from FDE to FDE it will be different. Okay, these are some original works of Neumann and his followers. Now let's consider another hyperbolic equation. Earlier we considered an elliptic equation, now hyperbolic equation, and apply the von Neumann stability analysis. I leave this as an exercise to you. Okay, homework. Dou E by dou t plus C into dou E by dou x is 0. Then if you form a FD by the FTCS scheme, you will get this difference equation. You apply the same stability analysis very carefully here and show that whatever you do, this is unstable. This FTCS scheme applied to this equation is unstable for all values of delta t and delta x. I leave it to you as an exercise. I'll take a small break now. Somebody is very desperate to call me. 2 minutes. I'll be back with you. Thank you. That was a call from admin, so I had to respond. Are you able to hear me now? Nandakumar?
Yes. Yes, sir.
Yeah, okay.
Yes, sir.
Yeah, okay. Yeah. So this is that homework for you. Let's go to 21. Stability of explicit methods. This is called as Lax method. Okay. Because this is explained by a person called Peter Lax. Now, if you substitute ut as dou e by dou t as u at I plus 1 plus u at I minus 1 by 2, average of the neighboring points I plus 1, I minus 1. Okay. Then what will happen? U at n plus 1, you maintain as it is. U I at n plus 1, instead of u at I, you put the average value. So you'll get another FD. Now to this, if you apply the von Neumann method, okay, same way, put the maximum error as this. Then e power a delta is nothing but am, right? It's called as amplification factor, which is cos theta c. You look at this. This is minus c is here. Okay. So you put the cos theta minus I c sin theta. C comes because of this, the C term, no, that's a Courant number there. Okay. So this capital C is actually minus C delta T by delta X. This term is calling as, sorry, C delta T by delta is calling as capital C, which we can call as Courant number or CFL, Courant Friedrich Louis. In short, we also call it as Courant number. Now you apply the stability requirement to this FDE. In the same way, you will arrive at a CFL condition. The condition states that if you want stability of the one-dimensional wave equation, then you can discretize dou u by dou t by this method, and the FDE will be there. Okay. So capital C is called as Courant number. The criterion is called as Courant Friedrich Louis criterion. Okay. It's called CFL criterion. Now it states that delta t is less than or equal to delta x by c for stability of hyperbolic equation. Okay. So this is one important condition when the equation is hyperbolic. If equation is hyperbolic, then also delta t should be less than or equal to delta x by c. Although I have not done the derivation, this result is very important. Now from equation to equation, you cannot keep doing this analysis, right? The value of c in practice, you have to find by experiment, whether your equation is stable or not. Okay. Anyway, it is good to know by theory. In theory also, we made some approximations in formulating, because we are not modeling the error up to infinite terms. We are doing only finite terms. Okay, because of this, we can get an idea of whether equation will be stable or not using all this analysis. Okay. Now let's continue. How many of you are taking hypersonic flow theory? Just an Sanjay, are you aware? Sanjay?
Yes,
Or anyone
sir.
else? How many of you are taking hypersonic flow theory? You have relative this time?
Sir, I think, yeah, yes, sir. Almost 20 of us have taken Hypersonic.
20 of you. Okay. In hypersonic flow theory, are you introduced to method of characteristics yet?
Sir, method of characteristics, actually, were introduced to that in compressible fluid flow, sir, but we just saw a very brief introduction. I think in detail it was in Hypersonic.
Oh, it is
I don't
done
remember.
already. It is done already. It's
Yes, sir.
covered, is it? So I don't have to cover it here.
Right.
Sir, can you repeat, sir, what you're doing?
Method of characteristics. There is a method. Are you? Are you taking hypersonic flow theory?
Yes,
No,
sir.
sir.
Okay, yeah. So I was thinking how much of it should be covered in this subject. Do you know the Ramanathan? Do you know the unit methods for method of characteristics?
No, sir.
Tell me briefly how much is covered for you in compressible flow. What is the method of characteristics? How much is covered? What was it which was covered?
Sir, name like that I have not heard, sir, in compressible fluid.
But Sanjay told it was covered in compressible fluid, so that's why.
Sir, Sri Krishna was explaining something about flow through CD nozzle. So,
Okay. Then
yes, sir. I don't remember in detail, but I remember he took a lecture on method of characteristics.
Sir,
okay.
we need a brush up anyway, sir.
Anyway, earlier we were solving those what equation? The characteristics lines we are seeing now. You are solving one this potential compressible flow, compressible potential flow.
Yes, sir.
So you are getting the condition that if m is less than 1, equation is elliptic, m is equal to 1, it
Yes,
is
sir.
parabolic, m is greater than hyperbolic. In that, you will have introduction to the method of characteristics. How did we define characteristic? Is a characteristic a line along which the variables are continuous, but the derivatives need not be continuous. Correct?
Yes, sir. Yes.
Now we can show that Mach waves satisfy this condition. Mach waves. So Mach waves we can take as something lines along with information flows, or practically these cannot be discontinuous. Theoretically there can be discontinuous. Correct? Sanjay, can you have dou u by dou x or dou u by dou something discontinuous in practice? No, right? Sanjay, is this having some problem? Ramanathan, Nandakumar, Anantakrishnan,
Sir, somewhat new, sir.
somewhat new.
New. Yes, sir.
Yeah. What have you have a Mach wave? What is a Mach wave?
Sir, Mach wave is very less compressed. I mean,
No. It's okay. What is the inclination of a Mach wave to the flow? Sine inverse of 1 by m.
sine inverse of 1 by m. Yes, sir.
Yeah. So in that direction, if you draw a line, that is a Mach wave.
Yes, sir. Yes.
We say that information propagates along a Mach wave.
Yes, sir.
Okay. Same thing mathematically, we'll say that something is constant along a characteristic line. The characteristic line is exactly a Mach wave if you look at it finally. Okay.
Yes, sir.
So the characteristic line, what I am telling is in characteristic line we defined as a line along which the flow variables are continuous, like u, pressure,
Okay, sir.
density, etc. But the derivatives are not continuous.
Yes, sir.
Okay. So we defined the line like that and got a line. We got the slope of a line
Okay,
for
sir.
hyperbolic flows only.
Okay, sir.
They don't exist for this one because your if you solve it, the delta, that is b squared minus 4ac for the
Forest.
equation, will be negative. So it doesn't exist for elliptic equation. It's equal to only one root for the parabolic type. There are two roots for hyperbolic type. Hyperbolic means Mach number is greater than 1. So at any point in Mach flow, there will be two characteristic lines, plus or minus theta, plus
Yes,
or
sir.
minus
Yes,
sine
sir.
inverse of 1 by m, along which both the characteristic lines exist. That is what it will tell.
Yes, sir. Yes, I understand.
Yes. How did we get this? You got something like numerator by denominator. We put denominator is equal to 0 and got this condition. Okay?
Yes, sir. Okay, sir.
Now, if physically, they have to be continuous. Correct?
Yes,
It's a
sir.
mathematical construct. So this is possible only if numerator is also 0. It will be 0 by 0 condition then. If it
Yes,
is
sir.
0 by 0, you can somehow apply L'Hospital's rule and apply at
Fine
a
limit.
finite limit. Yes. Same
Yes.
logic you think. If denominator is 0, practically the numerator also should be 0. Okay?
Yes, sir.
If you put the numerator is 0, you will get some condition. What does it say? If denominator is 0, then numerator also should be 0.
Yes, sir.
So, I'm telling, talk to the whole class, okay? Don't sleep off, please. So, if denominator is 0 means along a characteristic line. So, numerator is 0 will a condition. So, it will say that along that characteristic line, this condition should hold good. That's what it means. Understood?
Yes, sir.
Now, those conditions are what we will enforce in a method of characteristic. In hyperbolic equations, information can flow only downstream. Imagine supersonic flow. Information cannot flow upstream. Correct? It flows along these two characteristic lines at any point. And how does it flow? What information flows? There is a condition that numerator is 0. Okay, Anantha Krishnan? Anant?
Yes, sir.
Okay. Understood?
Yes, sir.
Okay. So anyway, we'll come back to this. I wanted to know whether I should conduct this method of characteristic for the class or is it covered already? That's why I started this discussion. Okay, next class we'll see. Whatever we are going to discuss next class is related to this. Anyway, it won't be very obvious here, but I can see that there are many common points in what is going to be discussed and the method of characteristic. Okay, so up to 21 we have covered today. Let me take attendance.